Welcome to Math for Infinity, where the world of mathematics knows no bounds. So today we are going to talk about convex functions, but probably before we start, if you are discovering this channel for the first time, well, better late than never, right? So I extend a warm welcome, a warm invitation for you to jump about our knowledge train, and whether you are eager to broaden your understanding of mathematics or participate in insightful mathematical debates or seeking help with your studies or whatever, right? Trust me, this channel is tailor-made for you, right? You have just found the perfect destination to fuel your curiosity. So feel free to subscribe now, right? In order to stay in the loop and become part of our growing mathematical community. So today's exploration is about convex functions, and as we dive actually into this topic of non-smooth optimization in infinite dimensional spaces, it becomes clear that the traditional derivative concepts that we explore so far in our latest videos fall short of meeting our needs. So many interesting functionals are not Gateau or Fréchet differentiable, right? You can think of let me just use another color. You can think, for instance, of the absolute value of x, right, which is not Gateau differentiable or Fréchet differentiable at the point 0. So we actually stand at a juncture, right, where captivating functionals actually defy the conventions of differentiation, particularly when it comes to functionals with values in the 2 points or 1 point compactification of R. So to overcome these limitations, we actually embark on a quest of a more versatile derivative concept. So one that goes, a derivative concept that goes beyond the confines of Gateau and Fréchet derivatives, yet retains the ability to uphold the Fermat principle, right? So, and of just a rich calculus. So in this lecture, we will consider a general class of functionals, right, that admit such a generalized derivative concept. So notably convex functions. And the generalized concept, the generalized derivative concept that I'm talking about is what we will later on in this lecture series, right, called convex subdifferential. So, but we are not yet there, right? So let's go one step at a time. Okay, so a proper functional, so this is a definition. Let me probably write it here. So a proper functional, a proper functional f defined from a Banach space X into the 2-point compactification of R. This is R bar, right? Is called convex. I think we defined already what proper means, right? This only means that the effective domain of the function f is non-empty, right? Or the infimum of the function f is actually finite. Okay, so such a functional is called, said to be convex if, this is what you know already, right? The definition is still the same. If f of lambda x plus 1 minus lambda y is less or equal than lambda f of x plus 1 minus lambda f of y. And this, of course, should hold for every x and y in X, and for every lambda between 0 and 1. Right? Of course, this function, the function value infinity is allowed on both sides, right? So, okay, so if, if for x different from y, right, and lambda between 0 and 1, right, so 0 and 1 are being excluded now, So if for these values, for these values of, for x different from y and lambda between 0 and 1, right, the open interval. So if for these values, we even have that f of lambda x plus 1 minus lambda y is strictly less than lambda f of x plus 1 minus lambda f of y, then we call f strictly convex. Okay, so an alternative characterization of the convexity of a functional f is actually based on its epigraph, right, which is encapsulated in the following. We say that we denote it APF, right? So this is our notation for, let me use another color. This is a notation to refer to the epigraph of the functional f, right? So this is nothing else than the set of points xt, right, x in the Cartesian product, such that we write it down here, f of x is actually less or equal than t. Okay, so of course, let's have a look at a couple of properties of the epigraph of a function. This is lemma 3.1. So let f define from x into the completion of R, right? This is R bar, right? Then the epigraph of f, right, is non-empty, right, if and only if it's non-empty if and only if the functional f is proper. If and only if f is proper, right? This is rather quite obvious, right? So, probably let's have a look at the proof, a very quick proof. If the epigraph of the functional f is non-empty, right, then this implies that, you can find a couple xt, right, such that f of x is less or equal than t, right? So this means that the infimum of the functional f, right, over x is finite, right? And this is exactly the definition of f being proper, right? So, and of course, if f is, yeah. Okay, so the reverse also holds. So there's really nothing to show, right? So, okay, so the epigraph of the function is convex if only if the functional f is also convex, right? So convex if and only if f is convex, right? This is also clear, right? Let's have a look at the, let's prove it. This is not really a proof, but let's try to say it geometrically. Oops. Okay, so say you have something like this, right? So just very quick picture. Good. So you have something like this, right? And then you have, say, something, oops, nope. Okay, so let me just style it a bit. Okay, say you have a function f like this, right? This is the function f, right, which is obviously convex, right? This is a parabola. Well, the epigraph is actually, the epigraph will basically be everything that lies above here, right? So this will be the epigraph of the function. Of course, we see that, the set defined by the point belonging to this area, it's obviously convex, right? So this will be epigraph of f, right? So, okay, so if your function is convex, then the epigraph is convex, right? So this holds. Okay, so our third property is that the epigraph is actually weakly or respectively closed, right? If and only if. So let me just write it. Weakly. So epigraph of f is weakly, respectively closed, right? If and only if. It's weakly or respectively strongly closed, I meant. If and only if the functional f is weakly, respectively strongly lower semicontinuous. Right, so well, if the function is lower semi-continuous, then the epigraph is closed, right? This is clear, right? So let me probably write it here. So this is kind of a short proof as well. So f lower semi-continuous, right? I just write LSC, right, for lower semi-continuous. This obviously implies that the epigraph of your function f is closed, right? This is clear. So this implication is clear. So for the reverse implication, you need to proceed by contradiction, right? So for the reverse, so this is basically the proof idea that I'm giving you. So for the reverse implication, proceed by contradiction. So this means, so you have to assume, so you have to assume that the epigraph of the function is closed, right? And that f is not lower semi-continuous, right? So saying that f is not lower semi-continuous means that you can basically find a sequence, right? Sequence of point in x, right, such that xn converges strongly to x, right? If you're dealing with weak lower semi-continuity, then xn will converge weakly, right? So here we are kind of I'm giving you a proof idea for strong lower semi-continuity. So there is a sequence such that xn converges strongly to x, right? And f of x is rather strictly greater than the lim inf of f of xn. Right? So proceed by contradiction, and then you just have to derive a contradiction. Okay, so so the proof, for the proof of GSM, I invite you to try it out yourself, right? So of course, if you face any issue, feel free to reach out to me, right? Or I'm looking forward to to read your comment, to read your question about the solution of this problem, probably, or the solution. So try it yourself. Okay, so however, a direct consequence of this lemma is the following. So this will be corollary 3.2. Okay, so let f, right, again defined from x into the 2-point compactification of R, right, be convex, right? Then, so let me just write, now we need our function f to be convex. Then f is weakly lower semi-continuous. Just write LSC, right? F is weakly lower semi-continuous if and only if F is, probably I use another color, F is lower semi-continuous. So here, so what this corollary actually says is that if you have a function that is convex, right, then weak lower semi-continuity and continuity do coincide, right? So this is the main essence of this corollary. So the proof is rather easy, right? So for the proof, so of course we just assume f is weakly. F weakly lower semi-continuous and convex, right? Assume that f is weakly lower semi-continuous and convex. Then by the lemma that we just prove, right? Assume that we prove that. Then the epigraph of the function f, right, is weakly closed and convex as well. Weakly closed because the function f is weakly lower semi-continuous, and convex because the function f is convex. So this is weakly closed and convex, right? So let me just write this equivalence followed by, so this is by lemma 3.1, the very first lemma of this lecture. And again, this is equivalent to saying that, that the epigraph for the function f is closed, right, and convex, right? But this actually follows by Mazur's lemma, right? We know that if you have a set that is convex, then weak closeness and strong closeness are equivalent, right? We actually went through that when we were discussing, we're talking about functional analysis. So I strongly invite you to check out my lecture series on functional analysis. I went through the Mazur's lemma, right? So this is by Mazur's lemma, right? So this Mazur's lemma basically says that convex plus weakly closed, right, is just equivalent to strongly closed, right? So basically the proof, Mazur's lemma basically says that if you give me a sequence, right, a sequence that converges weakly, then out of that sequence I can basically construct a strongly converging sequence, right? And that sequence is just made of convex combination of the xn. So that is basically the main statement of Mazur's lemma. Okay, and again, if we apply lemma 3.1 again, right, because so that if the epigraph for the function is closed, right, and convex, then the functional is lower semi-continuous and convex, right? So this is again by my 3.1, right? So just okay, so this will be the end of the proof, right? Because basically wanted to show that if the functional f is convex, right, then weak lower semi-continuity and continuity and lower semi-continuity is coincide. Okay, so another useful notion for the study of a functional f, right, the corresponding sublevel set, right? So we call it we denote those sublevel sets here by f alpha, right? So this is basically the set of point x in X, right, such that f of x always lies below alpha, right? So this is alpha in R, right? So this is sublevel set, just write it here. Sublevel set of the functional. Okay, F. Well, something that you probably noticed already is that sublevel set they look similar to the epigraph of the functional F, right? Just that here alpha is kind of fixed, right, up front. You can actually view the sublevel set of a functional F as the T section of the epigraph of F. So because the sublevel set looks similar to the epigraph, right, we have the following set of properties, right, that actually hold. So this is lemma 3.3. Okay, so let F again define from X into R bar. I think I'm getting tired already of saying F is defined from X to R bar, right? So, but well, that's fine. Okay, so let F, our functional, defined from X into R bar. X is a Banach space, right? So if F is convex, right? Then this corresponding sublevel set, then F alpha is also convex. You see that here we don't have an equivalence, right? Then this is convex for every alpha in R, right? But the converse is not true, right? So this is the warning here, but the converse is not true. Right? So to convince yourself, you can think of consider to convince yourself that the converse is not true. Consider the function f of x, right, equals square root of the absolute value of x, right? So basically you have something like this. Again, another sketch of the curve. So another sketch of the curve. So basically you have something like this. Let me just use this color probably. Yeah, this is just a sketch, right? So this will be the sketch of the function square root of absolute value of x, right? Of course, this is x, okay? So, well, you see that this function here is actually, sublevel set of this function are definitely convex, but this function is not convex, right? This function is not, it's not convex at all. Okay, so this will be a kind of a counter example, right? So, well, what else? Yeah, second property, just take, okay, good. So the second property is that F is weakly lower semicontinuous. F is weakly, respectively strongly lower semicontinuous, right? If and only if all sublevel set, right, are weakly or respectively strongly close. Okay, so I think the proof of this lemma is rather clear, right? Because quite similar to what we did with the epigraph, right? Because I told you that the sublevel set is, can be, they can be thought of as being the T section of the epigraph. So the proof is clear, right? So I invite you to take it. Okay, so now let's have a look at some example of convex functionals, right? So example of convex functionals. So the first example will be kind of the trivial example. So those are we use a different color. Those are affine functionals, right? So affine functionals of the form this is the dual pairing, right? So the duality pairing. For fix X star here is actually, it's a bounded linear operator, right? And alpha is just a constant. So affine functionals of this form, are obviously convex function. And second example will be what we use every day. The norm. Right? The norm vector space. We just write NVS to say norm vector space. X, right, is convex. The norm is convex, right? I invite you to prove it. And also, we also have the indicator function. This should not be confused with the characteristic function, right? So the indicator function, that you call delta C of X, right? And this is defined to be 0, right? If X is in C and plus infinity else, right? This indicator function is actually convex, provided that the set C is convex, right? Otherwise, it doesn't work. Okay, so as I said, a very good exercise for you would be to check that. Will be for you to check that that the norm is actually, is indeed convex. Of course, further example could be, constructed through the following operations. So this would be lemma 3.4. Yes. Okay, so let X and Y be non-vector spaces. NVS, right, for non-vector spaces. And let F again defined from X into R bar. Completion of R might be convex. Just highlight convex. Okay, then the following functionals are convex as well. Then the following functionals are convex as well. Okay, so the first one would be if you actually multiply f with a positive constant, then you still get the convex function, right? I mean, of course, if you take negative value of alpha, I mean, it will not work, right? Because you will rather this will rather lead to concavity, right? Which is, I mean, if I'm not wrong, of course, right? Which is not what we want. So for every alpha positive, if I multiply a convex functional by alpha, then I still get the convex function. So the second thing is that if you sum up to convex function, then you still get the convex function, right? So f plus g for g defined from x into alpha, right? Convex. I mean, this is again convex. The sum is again convex, and if you want to get strict convexity, then you only need one of them to be strictly convex, right? You don't need both of them to be strictly convex. Okay, so the third thing would be the composition. Phi composed with f, right? For phi defined from R bar into R bar, because we need to assure that the composition is well defined. So phi should go from R bar into R bar, right? Convex and increasing. So under these conditions, the composition is still convex. And the fourth property is that if you compose f with a, right? With a being a linear operator, right? So for a, say, defined from y into x, like linear, then this composition is still a convex function. And finally, the last point is that the map which at x associate the supremum of fi of x, right, over I, sorry, in capital capital I is an index set, right, arbitrary, with so with fi defined from x into R bar, right, convex for an arbitrary index set I. Okay, so of course the proof is trivial, so I'm not going to that. I mean, try it out. So I invite you to take it, right? However, before we proceed, I would like to draw your attention on the fact that this property here, property 5 here, right, actually implies that the pointwise supremum of affine functionals is always convex, right? Because we know that affine functionals are definitely convex, so this property ensures that the pointwise supremum of affine functionals is always convex. Okay, so this will be okay, the mat 3.4. Yes. So the mat 3.4, we say that property 5 that is this map here, so property 5, which was actually this property that I just wrote, for fi defined from x into R bar, right, convex, and I arbitrary, right? Implies, so property 5 implies in particular that the pointwise, let me use this color, that the pointwise supremum of affine functionals is always convex. Where I put it in color, it's always convex, right? And in fact, any functional can be indeed any convex functional can actually be written as pointwise supremum of affine functionals. Can be written, as pointwise supremum of affine functionals. Right, so I mean, to see this, I mean, this is rather, this is not a big deal. So let's have a sketch again. So say you have, right, so this is the frame, and again you have a function, say you have something like this. Oops. Okay, so say you have something like this, right? So let me style it a bit. Okay, so say you have something like this, right? So this is, say, your function f, right? So probably I put it in, yeah. So now to see that this convex function is actually the pointwise supremum of affine functionals, what the idea is just to actually to take at every point of the, I mean, of the graph of this function, to consider the, I mean, the slope at every point, right? The tangent at every point of this curve. So you will get something like this. Or like say you will get something like this, right? So this will be an affine functional. Let me style it, right? And again, I will just duplicate this thing and then, oops, and then do something like this, right? Yes, let me style it. Let me use a different color. Okay, now duplicate this one, and then, I mean, you're just taking the slope, right, at every point. So this is how, and then from this, I think it is quite obvious that, oops, duplicate. Right, so basically you, I mean, it's only about taking the, I mean, as I said, just kind of consider the slope of, okay, so you basically have something like this, right? And I think from this picture, it's actually, it is rather clear that our convex function f is actually the pointwise supremum of affine functionals, and those affine functionals are just the slope, right, of the function f at kind of every point, right, of the function, I mean of the graph of the function. Okay, so well, but don't worry, we can show this kind of analytically, right? So to show this, we define for a proper functional f, we define what we call the convex hull of the function f, right? Or probably know it under the name of the upper envelope of the function f. So so we say that the convex hull of a function f, right, defined from x into r bar, right, is defined by we denote it f gamma of x, right? This is the supremum, right, of ax, right, such that a is affine, right, and a always lies below the function f. So with a x tilde, let's record an f of x tilde for every x tilde in x. So this is how you will define the upper envelope, right? Or the convex hull of a functional f. And of course, note that f gamma is actually defined from x into minus infinity plus infinity, right? So this supremum can be plus infinity or minus infinity, right, depending whether it is empty or not, right? So okay, so lemma 3.5, right, basically, so lemma 3.5 basically says that if you have a functional f, right, defined from a Banach space x into the compactification of the 2-point compactification of R, right, which is proper, right? Proper means that the effective domain of the functional f is non-empty. Then f is convex, and lower semi-continuous. Just write LSC, right, for lower semi-continuous. If and only if, let me just write it this way. If and only if f is coincide with its convex envelope, with convex envelope or convex hull, right? Okay, so let's prove this. Proof. I think the reverse implication is okay, right? I think this is okay, right? Because if you have, if f actually coincides with its convex envelope, then f is obviously convex, right? And also lower semi-continuous, because we actually saw that the supremum of lower semi-continuous function is always lower semi-continuous, right? But it doesn't work with continuity, right? If you have a sequence, a family of continuous function, then the supremum of that family may not be continuous. So, but it works with lower semi-continuity. So this is okay. Since just write y, since affine functionals are convex and obviously continuous, right? Convex and continuous, and in particular lower semi-continuous. So it follows from, I think it was lemma 3.4, property 5, right? Follows that the pointwise supremum, that f gamma, right, which we hide as the supremum of so as not to get you lost, I'm just defining it this way, right? So that this, the dot is just a placeholder, right, for the argument of f gamma. So this is the supremum of affine functionals, right? Such that A is always lies below F, right? So this F gamma is convex, right? Right, and of course by lemma 2.2, right? Maybe we saw that. I mean, this was also part 5, right? Yes. So I invite you to watch out to check out my previous video on differential calculus on this lecture series, right? So by lemma 2.2, right, F gamma is also lower semi-continuous, right? As supremum of lower semi-continuous functionals. Okay, so this would be the proof for the reverse implication. Now, for the direct implication, I mean, if you assume that our function f is proper, convex and lower semi-continuous, so now let f, right, defined from x into r bar be proper, convex, and lower semi-continuous. Then by definition of the convex Hull as a supremum, then by definition of F gamma, it is clear that F gamma is always less than F, right? Because F gamma is actually is composed of affine functionals that always lies below F. So F gamma is always less than F. So it remains to prove that F is actually less or equal than F gamma, right? In order to conclude that they are equal. Okay, so for this, this is still just the sketch of the proof. So for this, we proceed by contradiction. So the first step is actually proceed by contradiction. Assume that the inequality doesn't hold, that F gamma is rather strictly less than F, right? So this means that there exists a point x0 in X, right? And there exists also, lambda in R such that F gamma of x0 is actually strictly less than lambda, which is strictly less than f of x0. Okay, so now the goal, the idea here is actually to apply the Hahn-Banach separation theorem. So in second step, we apply the Hahn-Banach separation theorem, right? So that's why I invite you to check out my lecture series on functional analysis, right? I went through, I think it was actually the very first video of this channel, right, where we discussed the Hahn-Banach theorems and friends. Okay, so we apply the Hahn-Banach separation theorem, right, to construct a hyperplane, to construct an affine functional by hyperplane, right, if you want, an affine functional, call it A, right, with A less or equal than F, right, but E of x0 being strictly greater than lambda. Let me just drag it a bit here, which is strictly greater than f gamma of x0, right? Which, I mean, if you do this, then we get a contradiction, so which would contradict the definition of f gamma, right? Because f gamma is actually the supremum of affine functionals that lies below f, right? And here you have an affine functional that comes from the Hahn-Banach separation theorem, that lies below f, but somehow is actually greater than f gamma of x0, right? From this, but this doesn't make sense because, I mean, this should always, by definition of f gamma, as being the supremum of such functionals, this inequality should rather be in the reverse direction. So this would be the contradiction, right? So, well, okay, well, I just said apply Hahn-Banach theorem, I mean Hahn-Banach separation theorem, right? But I mean, we know that the Hahn-Banach separation theorem actually involves two sets, right? One that needs to be compact and the other one to be closed, right? So what are those sets? So we just need to define the set A to be the singleton x0, lambda. I mean, this is just a compact, right? It's a singleton. And you take B to be the epigraph of the function f, right? Which is closed and convex, right? Because we have the assumption that our function f is actually proper, convex, and lower semicontinuous, which is closed and convex, as f is assumed to be lower semicontinuous and convex, right? And then we saw that, I mean, we can actually, from the convexity or the lower semicontinuity of the function f, we can actually say something about the convexity or the closeness of the epigraph of the functional f. Okay, and then you have the set A and B, right? One is compact and the other one is closed, right? So we are in the setting of the Hahn-Banach separation theorem. And again, of course, the intersection of A and B is empty, right? So those are two disjoint sets because f of x0, right, is actually assumed to be strictly greater than lambda. So this point, I mean, x0, lambda is not an element of the, of the epigraph. Okay, so this will be the end of the proof. So, of course, I mean, feel free to write it fully and properly if you want. And again, if you have any problem, any issue, feel free to reach out to me. Yeah. Okay, good. A particular class of convex functionals in calculus of variations arises from integral functionals, right? With convex integrand defined through what we did in our last lecture, superposition operators. So let's have a look at the mark 3.6, which basically tell us in which case we can actually, if you have, if I have an integral functional, right? In which case, on which assumption on the function f, right, can I conclude about the convexity of the integral functional. So this is lemma 3.6. So let f, now we talk about it f, right, defined from R into R bar, right, be proper, convex, and lower semicontinuous. So probably, the question for you, is this function little f continuous? So drop your answer in the comment. I will check it. So let little f defined from R into R bar be proper, convex, and lower semicontinuous. If omega, right, is actually a subset of Rn is bounded, right, and P is actually between 1 and plus infinity, so we have a bounded domain omega, and we have P between 1 and plus infinity, then the integral functional f, right, defined from Lp of omega into R bar, right, which maps u to the integral of omega of f of u of x dx, right? This is if f composed with u is actually in L1, right, and plus infinity else. Let me just highlight the condition. Okay, so then this integral functional is also proper, convex, and lower semicontinuous. So let's have a look at the proof. By the way, a typical example of this of an integral functional of this form will be the L1 norm, right? Like when f is equal to the absolute value, right? So you get that capital F of u is actually say the L1 norm of u, right? So yeah, so this would be a typical example, for instance. Okay, so proof. So we first start with properness, right? We want to show that our integral functional f is proper. So properness. So I will start first by showing that function is well defined. So which will be helpful also a bit later on. So since f is convex, right, and lower semicontinuous, well, we know that f coincides with its convex hull, right? This is by lemma 3.5, right? So this means that there exists a alpha, in R, right? I find some constant in R such that f of t is actually greater or equal than at minus alpha, right? Because if f actually coincides with its convex hull, right, then and then you know that the convex hull is actually means the pointwise supremum of affine functionals that actually lies below the functional f, right? So because f equals f gamma, you can find an affine functionals that actually lies below the function f, and this is affine, right? This is an affine functional, at minus alpha, affine in t, of course, and this is for every t in R. So this means that fu of x, right, is greater or equal than a times u of x, right, minus alpha, and this is of course for every u in Lp of omega, right, and for every p greater or equal than 1. So this means if I take the integral, so this on both sides, so this means the integral of f of u of x dx, right, is greater or equal than the integral of omega of a u of x a times u of x, right, minus alpha. dx, right? Now, observe that this quantity here is exactly f of u of x, right? I mean, probably f of u, let me just keep it this way. And this quantity here is actually, I mean, it cannot be minus infinity, right? Because as omega is bounded, yeah. And you know that, I mean, as omega is bounded, we know that LP of omega is actually contained into L1 of omega. Okay, so this basically says that f of u is actually, I mean, it's not minus infinity, right? No matter u, LP of omega. So moreover, since f is proper, right, there exists T0, right? I mean, properness means that the effective domain of the function f is not empty, so there exists a T0 in the effective domain that I denoted dom f. There exists T0 in the domain of f. Now, as omega is bounded, I mean, the assumption on the boundedness of omega is actually very important. As omega is bounded, I mean, if you set u0 to be a constant T0, right, which obviously belongs to the domain of capital F, right, then you get that f of u0, right, equals to the integral of omega of f of t0 dx, right, which is of course finite, right, because I mean, f of t0 will be is constant in t, so you can put it outside of the integral, and then you just have, I mean, something that is proportional to the volume of to the best measure of omega. So hence f is proper. Okay, so now let's move to convexity. I think convexity is rather trivial, right? So I will not go into that. I mean, it's only about applying, I mean, using the fact that little f is convex, and then you just distribute the integral. I mean, use the linearity of the integral. Yep. Okay, so now let's move to probably the last part. I mean, lower semicontinuity. Okay, so for this we use so to prove the lower semicontinuity of our integral functional, we will use lemma 3.1. So for this, we use lemma 3.1, which basically says that our integral functional is lower semi-continuous, right? If and only if its epigraph is actually closed, right? So it is actually enough for us to show that the epigraph of f is closed, right? So and then we are done. Okay, so we use the sequential characterization of closeness, right? So let un comma tn, right? So let this be a sequence of element of the epigraph of f, right? Such that un converges to u in LP of omega. So you have strong convergence, and Tn converges to T in R. Right? So what you want to do is that you want to show that UT, I mean, is actually in the epigraphs. So you want to show, you want to prove that u, comma t lies in the epigraph of our integral functional f. Okay, so for this, it's not difficult. So as un actually converges strongly to u in LP of omega, right? There exists a subsequence, right? That we call unk, right? Such that unk of x actually converges to u of x, right? For almost every x in omega, right? I mean, strong convergence actually implies pointwise convergence, right, of a subsequence. So hence, lower semicontinuity, probably write it fully. Hence, lower semicontinuity of little f, right, together with Fatou's lemma implies that, so if you apply the lower semicontinuity of little f, then together with Fatou's lemma, you get that the integral of omega of f of u of x, right, minus a times u of x minus alpha dx, right, that this is actually less or equal than the integral over omega, right, of the limit, I mean, of the lim inf, right, of f of unk of x, right, minus a times unk of x minus alpha. So let me just drag it the left. Yeah, to get this dx, right? So, and now observe that at the very beginning we actually, so we are basically applying Fatou's lemma with this sequence here, which is actually greater or equal than 0, right? Due to what we saw above, right? That little f coincide with its convex envelope. So, okay. So now if you apply Fatou's lemma, so this is less or equal than, so this is by Fatou. The first step, I mean, the first inequality actually follows from the lower semicontinuity of little f, right, and the linearity of the integral. So now if you apply Fatou's lemma, then you get that this is less or equal than the lim inf, right? Forgot plus infinity here. I mean, when k goes to plus infinity, maybe I should hammer that. Yeah, when k goes to plus infinity of the integral over omega, right, of f of unk of x, right, dx. And now on the other side, I will just apply the limit, right? So minus the integral of omega of a times u of x minus alpha dx, right? So now, well, this is actually less or equal than the lim inf. I can basically actually write this as, I mean, this corresponds to our integral functional. So this is the lim inf of f of unk, right, minus the integral of omega of a times u of x minus alpha dx, right? Now, because unk tnk is actually in the epigraph of the functional f, right, this is less or equal than the lim inf of tnk, right, when k goes to plus infinity. I said this is because as unk tnk, right, is in the epigraph of the function f, right? Being the epigraph means that f evaluated at u and k is actually less or equal than t and k. So that is why you have that this is less or equal than lim inf of t and k, right, minus the integral over omega of a times u of x minus alpha dx. Okay, but this actually goes to t, right? Because we saw that Tn actually converges strongly to T. So all the subsequences, I mean in R, all the subsequences converge to the same thing. So so this means, now observe that on this side you have this term here, right? And if you go a bit up, you will see that we also have this term here. So we can basically cancel that out, right? And then we get that f of u is less or equal than t, right? Once ut is indeed in the epigraph of f, right? So this means that the epigraph of f is closed, right? And this actually is enough for us to conclude that our functional f is actually lower semi-continuous. Okay, so this was actually, I think we are going to stop here. So yeah, thank you for following along. Yeah, and until then, stay safe, stay curious, and see you in the next video, hopefully. And of course, don't forget to subscribe, right? And yeah, if you want to be part of our mathematical community and kind of improve your mathematical understanding as well. If you have any issue, if you need help with your homework or anything, feel free to reach out to me. So thank you once again and see you in the next video.